Hey, good morning, students. And today we'll be looking at a very classic machine learning algorithm. It's called naive Bayes. And today we'll be working based on the Gaussian distribution, right? So the idea of naive Bayes is actually very simple. Given some distribution, you're trying to predict some new samples. For example, here we have four distribution of four classes, um, uh, and X could be one feature, for example. And you can imagine this graph can be in 2 dimensions in which it becomes an actual mountain, right? But here, to simplify, we have some feature, and based on that feature, you have the distribution of each class, right? So you can see that for the class of the green classes, the mean of this feature X is mostly around, let's say, minus 2.5, right? And but for a class of the blue, most of the samples lies in the mean of 0, right? For this feature, right? And yeah. And this is a very, very nice distribution of four classes. So now, let's say I have samples that have a feature X of 2. What is the probability that it should belong to green? Well, if you just take green and hit here, it's almost 0, right? If you try blue, it's also almost 0. If you try red, I'm not sure, it's like 0. Almost 0.1. And if you try 2, is around 0.1, right? Almost there, right? So to conclude, once we have this distribution, if that sample X have the feature of this one of 2 here, then there's a very high chance that is belong to the class of yellow, right? So this is just basically the whole idea of naive Bayes, right? So the idea is you have to first create a distribution of each classes. To create it is very simple. You just need 2 parameters. That is the mean, which represent the peak of each of the normal distribution, and the standard deviation, which represent how spread the distribution. And based on this, you can then try to predict the given samples, right? So that is the whole intuition. Now, let us take a look at this very famous naive Bayes formula, right? In which it states that the probability of that X, right? Sorry, the probability of Y, right? So the probability whether it should be class 1, 0, 2, 3, given that X, right? So basically it's the same question I'm trying to ask, right? I have some X tests and I'm trying to predict the probability of Y, right? It's basically equal to, according to the naive Bayes equation, is basically the probability of X given Y, right? And what is this? The probability of X given Y is basically this normal distribution, surprisingly. And then the probability of Y, right? And divided by probability of X, all right? So this part could be, it will not be so friendly for those who are not so comfortable with mathematics, but let us try to do some coding to understand each of the part, right? So let us take a look at the outline of today. So today we will try to understand what is this Py. We'll try to understand what is this Px given Y. And we will try to multiply them together. And in fact, we can already predict. The reason why we can already predict is because we can ignore this bottom part, right? Because if for that given Y is bigger than another one, you can already cancel the bottom part anyway, right? So if you multiply the top part, you can already predict which class there's a higher chance, right? And then we will have some real implementation. So here I already prepared some data set in which I simply make some classification and splitting train test set and scaling. Notice that I did not add intercepts because it's not required in this naive Bayes setup. And then basically calculate the mean, blah, 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 and then try to calculate the accuracy. All right. So without further ado, let us start right now. So what is this probability of y? Well, it's actually very simple. So let's say I have X train. Okay, wait. First of all, let me just make sure I run this. Okay, so that I have NP. And let's say this is my first sample, my second sample, my third sample. All right. Oh, sorry. All right. And then here's my X test. Right. So what is the idea? The idea is that I have these samples, right? And I want to, of course, I haven't even specified what are the class of each one. Okay, why not we do it now? So Y train is equal to np.array 0, 1, 1, 0, right? So the idea is that, okay, we know this and this belongs to class 0 and this both is belong to class 1, right? Now, based on this, you should be able to create this distribution of class 0 and 1. You can easily see that 0 and 0 is this one and this one. So what is the mean of this feature? Well, 1.5. What is the mean of this one? 3. And what is the mean of this one? 4, right? So based on that, we can already create a three-dimensional, let's say, normal distribution, right? And based on that, we can just put this guy inside and see which one has a higher probability, right? But before that, let us make sure we understand this PY. And of course, Y test is equal to np.array. So this is just my ground truth or my test, right? So now what is PY? The probability of Y is extremely simple. It's simply the priors, let's say M0, right? That is the number of X train in which Y train is equal to 0. And we're going to do the same, which is M1 is equal to this one. And we're going to print M1, right? So it seems like we got two samples for each. And prior is nothing but equal to M0 divided by M0 plus M1, right? Extremely simple. Right. So it seems like, so the prior is nothing but the probability of each classes, right? How likely is 0 and how likely is 1. So yeah, congratulations. We are able to figure out this probability Y, right? So now we are able to now figure out this PX given Y. All right, so give me 1 second. Okay, I cannot. Okay, I should be able to close this. Give me 1 second. All right, good. So now, how do we calculate this px given y? And in fact, the px given y, this x, right, should belong to each of the feature, right? Because we cannot do for all the feature at the same time, so we have to do for each feature first, right? And then the y could be for the class 1 and the class 0, right? And finally, the total probability, because we are based on each of the feature, we just multiply all the features, and then we can have the total probability, right? So great. So let's do this right away. So first of all, let us calculate. In this formula, it looks very difficult, but you can see that there's a we have to calculate this mean and standard deviation belonging to that feature, right? So based on our data, so for example, X train, right? What it should give us is that for class 0, it should give us 1.5 for here, for this feature 1, and 3 for feature 2, sorry, and this one is 4 for feature 3, right? So that is something we want to create, and that would represent this number, mu. And of course, based on that number, we also need to create a standard deviation. All right, so let us create a function, x, y, k, and n is equal to x dot shape 1, right? So this is the number of features, and okay, and let us make sure that what do we want, right? We want this to return us the mean and standard deviation whenever we call this function, and we want to pass in the x train, the y train, and then the k equal to 2. That is, we already specify how many distribution actually it has. Based on that, we can create a mean, and the shape is nothing but k comma n. So what does this mean, k comma n? Well, so like I said, we need the mean of this one, right, and this one, and this one, right? So this 3 is basically k. Sorry, this is the feature, right? So this will represent this number n, right? But how many we have for that? We have k of that because we have to do for class 0, and we also need to do for class 1, right? For the mean, right? So this could be probably the right shape for us, right? But by the way, it should be like this. How about the standard deviation? And it's the same, right? And now we can now try to calculate the mean, and this is all Python code, right? For label and range k, right? Mean label, right? So mean of class 0 is nothing but taking the x in which the y of that is equal to that class, and then mean them across basically the feature, right? And the standard deviation is the same, right? Right, and yeah, and probably, and that's it, right? So returned mean and standard. So great. I think we should be able to run this, and we can get the mean and standard deviation, and you can see that this is perfect, right? Like I said, for class 0 is 1.5, 3, and 4. For class 1 is this, and this is the mean, and this is a standard deviation. Perfect, right? So again, the reminder is how do we use this, right? Well, this will be used later on in this part, the mu and the standard deviation, right? Also this one, standard deviation. And this one, once you plug all the numbers here, you will get this normal distribution, right? And after that, what is so amazing is based on that normal distribution, if you plug any x, right, and this x could be belong to a test set, you can get the probability of this x, right? So this is the utility of this Gaussian distribution, right? All right. So now we got this mean standard deviation. We want to now create this formula, right? So we can say Gaussian PDF, right? Probability density function for short. X mean this one. And what do we want? Well, we want px given y 0 equal to Gaussian PDF x test and send in the mean of class 0. Actually, this should be fine. And that. And also we want to get the px given y 1, right? So what is this? This is basically this part, right? But the x is actually test set. We don't need the training set. The training set is already used for creating this distribution, right? So you can see that the training set create this mean and standard deviation, and that's it. This is the training protocol. There's no more training, right? The training is just the fitting the fitting protocol is just to find the mean and standard deviation, and that's it, right? And then you can now predict it right away using this function. So similarly, right? And I gotta send in mean 1 in, right? So now I will have two probabilities, right? Px given y0 and px given y1. And if I compare them, I should be able to know which one has a higher probability of this given x, right? But of course, I need to multiply according to naive Bayes. We have to multiply py first, and then we can compare accordingly. Again, we don't need to, we can ignore p given x because they are the same anyway. So we can just cancel them when we compare, right? So to do this, the left part, right? So I'm gonna do the left part and the right part. You can scroll up and down and see whether I do this correctly. But I will just to make sure I don't type anything incorrect, I will just copy paste what I already prepared. And this part is on the left side, and this part is on the right side. And basically the right side is basically together with the E. And then I return left times right, right? You can pause the video and then type along me. All right, so now we got this px given y0 and px given y1, right? So let us take a look at how does this look like. So px given y0. So what does this number actually mean? Okay, so why not we do something nicely? So we're gonna say np dot set print options to make it look small, suppress equal to true, and so that the numbers are better. And so what does this mean, right? So you have to understand the meaning of this, right? So what is our x test? First of all, you have to take a look at our x test, right? And that is the first sample and the second sample, right? So 0.483 right here means the equal to the probability of first sample belonging to class 0, right? Based on features 1, right? Basically, that is the idea, right? And similarly, 398 is equal to the probability of the first sample belonging to class 0 based on feature 2. So you can see that we cannot judge whether this sample belongs to class 0 only based on one feature. There's a probability of each of the feature, right? So this is a very important aspect you need to know, right? So now, what is this 0? This is the same. This 0 is the probability of first sample belonging, sorry, the second sample, right? Which are the second sample, right here, 7, 8, 9, belonging to class 0 based on feature 1, right? So this is the idea of px given y0, and it's magically provided once you use this formula. So to review, what do you do? Well, you find the mean and the standard deviation based on the training set, and that's it. And then you just plug your x test into here. You already get the probability of whether it should be belonging to class 1 or 0 based on each of the feature. Right. And of course, I can also type 1, and then I will see the same thing, but for class 1, right? All right. This is excellent. So now, based on this, you may ask me, how do we then come up with one number, whether it should belong to class 0 and 1, and that is based on we can take the product of, so we can multiply this one with this one and this one, we'll get one number, and that is the probability of first sample belonging to class 0, right? Based on average of all the feature, right? And this is for those who don't understand why product, I mean, because they are, each of the feature, they are not related, so whether they will be contributing to the same event is basically multiplying all of them together, right? So the total likelihood of the class 0 is equal to NP dot product Px given y 0, x is equal to 1, and similarly this one for 1. All right, and let us print them out. So now we got the probability, right? So once we take this, multiply this with this, we get this number, right? That sample 1 belonging to class 0 is this. And when you multiply these three numbers together, you got this, right? So you can already answer which sample should belong to class 0, right? And that is that. If you go to 1, you can see that sample 2 has a much higher probability than the first sample when it comes to class 1, right? Great. So once we have that, we can conclude by multiplying them to py, right? So if I multiply this one, by the way, we call this posterior equal to prior 0 multiplied with this one, which we already calculated earlier, and I'm gonna call this 0. And 1. Right, so we can see this is the final probability. So we must multiply with prior 0, and it looks the same because our prior is basically 0.5 and 0.5, and similar for 1, right? Now, how do we predict? Well, the prediction is extremely simple. We just say that y hat is basically 1 times a posterior 1 greater than posterior 0. And this may look very difficult, but actually you don't need to write the formula like this. And you can just say that, okay, for the fast sample, it does not belong to definitely class 1, right? And this is definitely class 1, right? Okay, good. So so the prediction is extremely simple. So hopefully you understand what is naive Bayes, right? So naive Bayes, the intuition is you got this Gaussian distribution, and then given unseen x, you try to put them in here and try to see which distribution it likely belongs to. And to do that, you just use this formula, and this one, Px given y, is basically just calculated by Gaussian distribution, right? The common question you may have then is, can I use a different distribution, not Gaussian? And the answer is yes. So that's why this algorithm is called naive Bayes in the Gaussian distribution, right? So hopefully now you understand the naive Bayes. Now let us try, why not we put them into real data. So here I'm creating some data, and I have some X train and X test again, and I want to see whether this is gonna work for naive Bayes. So let us calculate the mean and the standard deviation. And this time, because I already have all the code up there, I would just copy paste. And then, so this code is basically the mean and standard deviation. And these are the probability density function. And this is nothing but right here, right? And then we calculate the likelihood of each of them. So firstly, I calculate the Gaussian PDF of them. And then now I basically, here I'm just writing some a simple test case to make sure things are correct. And finally, now I can calculate the total likelihood by just simply taking the product. And then I can also calculate the prior, right? And then finally, I can calculate the posterior, which is basically the multiplication of px given y and py. And finally, I can predict the accuracy, which is so the y hat is basically this one. And then now I'm just gonna use classification report and average precision score. And you can see that naive Bayes is not so bad. I got the score of around 0.77. And so we are doing quite well using naive Bayes, given that this data is not exactly separatable, right? So yeah, so try to take a look at this code and try to see whether you can run them and make it work, and then try to maybe go slowly, a little bit slowly, and check whether you understand fully. Yep. Thank you very much. Bye-bye.